All right, I'm back. We're still on 302. We just went through this monster problem here, which was a pure delight. One of the things that's useful about derivatives, right? You want to be able to find where they're equal to 0, also where they're undefined. So if you look at the derivative we just found, definitely undefined at x equals 0. Can I find the zeros of this derivative? I think that it would be very challenging. It's not even a quadratic. I'm not really sure what I would do. I'd probably just use a calculator at that point. And then it's like, why did we bother doing it? I don't really know. For practice in our case, right? But if you're going to use it, like calculator all the way. All right, let's keep going. So we want to find the derivative. So remember, product rule. It's going to be first derivative of the second plus second derivative of the first. First derivative of the second plus second derivative of the first. First derivative of the second plus second derivative of the first. If I had to do this problem, I would actually just expand it and power rule it straight through. But that's not what we're doing here. So what we're doing is we're using product rule. So the function is called z, right? That's the dependent variable, and the independent variable is t. So the derivative, I could just say z prime. But to get better used to the other notation, I'm going to call this dz dt, right? Rate of change of z with respect to t, dz dt. So let's do that. We got dz dt going to be first, which is t cubed. Derivative of the second, derivative of 3 is 0, and then minus 4/3 t to the 1/3 plus second, which is, am I going to fit this? Barely. 3 minus t to the 4/3, derivative of the first, which is 3t squared. Okay, so that's first. Here we go. Let's highlight some things. First, derivative of the second, plus second, derivative of the first. All right, let's say it again. First, derivative of the second, plus second, derivative of the first. Okay, so color coding a little bit. I know that using colors is really helpful. I mean, when we're in the classroom, I pretty much exclusively have access to a black marker. Here, I have more options, but it's like hard to remember to change, but I think that it can be very helpful. All right, let's expand this. So dz dt. So it's z is the dependent variable, t is the independent variable, so it's dz dt is negative 4/3. Ugh, threes, they're my worst. 3t to the, so it's 3 plus 1/3, so 9/3 plus 1/3, 10/3. 10/3. And then plus, we're going to distribute here, so 9t squared minus 3t to the 6/3 plus 4/3 is 10/3. Okay. All right. Common denominator, I suppose, would be 3. Should I even do that? I don't know. Should I get a common denominator or should I factor? Like, what should I do? I'm gonna go with a common denominator for like no, I don't know. Factoring would probably be better, but whatever. Negative 4t. Basically, you have to make a choice and just live with it. And then I'm gonna probably end up factoring this. I don't know what I'm doing. I mean, I you know, oh my God, imagine if I didn't know what I was doing at all. Like, what is your what education are you even getting? I don't like that. I don't like that exponent there. 10/3 over 3. All right, so I have 27t squared minus 13t to the 10/3 over 3. Okay. So should I factor anything out? Like I could, so it's 6/3. I could take out t to the 6/3, which is t squared. So I could do t squared, and then 27 minus 13. I took out t to the 6/3, so there'd be t to the 4/3. Oh, there's no t there. T to the 4/3, and then all over 3. That might do it. Let's call that dz dt. Oh God. dz dt. Let's go to the calculator and see what the calculator says. So one of the things that I try to do is I try to write them in ways that I think the calculator will write them. It's like a nice little challenge for yourself. So we're gonna find the derivative with respect to t of t cubed times 3 minus t to the 4/3. So what did you do? You took out negative t squared, which gave you this. I don't know. I'm talking to the calculators if it's a person here. That's how long this has been. This is my life now. I'm talking to calculators, talking to iPads. Yeah, same answer. So good job, us. All right, let's go back. Let's do one more, and then I'll split this page again. It's gonna be a 3-video page. That's crazy. All right, let's see. Oh, this one? Yeah, we got this. So this will be, remember, your product rule. So it's going to be, we got a first function and we have a second function. It kills me. There's a rule called the product rule. And then people see a product of functions and they think they can find the derivative some other way. No, use the product rule. It's called the product rule for the derivative of, guess what? A product, right? This is a product. So option number 1 on this is to expand and just power rule it, which actually I would probably do. Actually, no, this one, I'm on the fence. Let's see how it goes. So f prime is going to be first derivative of the second plus second derivative of the first. First derivative of the second plus second derivative of the first. All right, let me highlight some of those. First, I'll switch as I go. Derivative of the second plus second. Wrong color. Dang it. Okay. Second. Derivative of the first. It's too hard, man. Switching the colors. Not hard to say. First derivative of the second plus second derivative of the first. First derivative of the second. What times? What? First derivative of the second plus second derivative of the first. First derivative of the second plus second derivative of the first. Say it over and over. All right, what can we take out? Obviously a 2x. There are birds just going nuts outside. It's like a really nice spring day, feels like. 2x can come out. That'll give me x squared plus 3 plus x squared minus 8, which gives me 2x. 2x squared minus 5. Call that f prime of x. I think that's good. So I'm going to stop that. I'm actually just going to stop there, right? So if I needed the zeros of this, x equals 0, definitely. Also, you get 2x minus 5 equals 0, x squared equals 5 halves, x equals plus or minus the square root of 5 over 2. So you can go from there. You could have expanded this and then taken the derivative from there. I will say, with these kinds of things, it's almost, the product rule works out incredibly well because the derivative of the first and the derivative of the second are equal to each other, so you know you're going to be able to like just factor that out. Really interesting too. Like if two functions have the same derivative, then what does that mean about them? So they have the exact same basic shape. What you don't know is like the y values. So if two functions have the same exact derivative, it means that the functions are just vertical shifts of each other, which is definitely the case here, right? So x squared plus 3 is a quadratic with a y-intercept of 3. X squared minus 8 is the same quadratic. It's just basically x squared, but with a y-intercept of negative 8. So one of them shifts it up 3, one shifts it down 8, but they have the exact same shape. So there's no reason the slope wouldn't be the same at every x coordinate. It's just that the y values will be different. But derivatives aren't really about y values. They're about like rates of change, slope, the overall shape of the curve, but not where it is with respect to the y-axis. But anyway, I'm going to end this one here. I'll be back to cover the next two, and then we'll keep going from there. Hope you are finding these sort of helpful.